In the name of God, the Compassionate, the Merciful, Engineering Plasticity course, Chapter 1, Introduction, Part 2. Now then, we spoke about tensile test in Part 1, and here we continue with the result of the tensile test. Now, as you can see in this figure, we have the initial part of the tensile test results. Here we have the stress, here we have the strain, and as it is shown here, the elastic deformation finishes here. Obviously, we know what elastic deformation is and what plastic deformation is. Elastic deformation is a linear behavior, and plastic deformation is nonlinear deformation. Elastic deformation is recoverable, plastic deformation is not recoverable. Plastic deformation is a permanent deformation, elastic deformation is not permanent and could be recovered upon removing the load. So here, as we can see in the figure, this point P is the proportional limit, and after that the plastic deformation starts, but there is no distinct point telling you where the elastic deformation finishes and where the plastic deformation begins. In fact, the yield points is not clear on this curve. We don't know where it is. We don't know whether he is here, is there, or there. But on this curve is very clear distinction between the elastic behavior and plastic behavior. In fact, this kind of behavior exaggerated here is for the mild steel results of the tensile test. For the mild steel, we have an upper yield point and a lower yield point. And so the sigma y shows the lower yield point, and we can see the plastic deformation after that. Therefore, this area is the yield point area. And we recognize this very clearly when we draw the curve for the stress-strain results for the mild steel. But for aluminium, for instance, it's like this. We cannot distinguish where the yield point lies. So what we do is that on the strain axis, because the strain is dimensionless parameter, okay? So because the strain is delta L over L, is L minus L0 over L0. So no dimension, dimensionless. We move about 0.2% in here, and then we draw a line parallel to the elastic line, okay, parallel to this line. Wherever it touches, intersects this curve, we say this is sigma y. This is the yield point, okay. That's how we determine the yield points for the materials which do not have a distinguished yield point like this, okay. And how have we come to this 0.2% number? This is from the experience, okay. Experience shows that most of the metals showing behaviors like this yield at 0.2% on the strain axis, okay. So that's the difference between materials showing the yield point and not showing the yield point. In this figure, again, we are showing a stress, and here is strain. But here we are showing engineering stress. Engineering stress, that is the maximum tensile strength, UTS, showing here by M, Uh, of course, this is the engineering stress strain, and this is true stress strain. What's the difference? Why does it show this behavior and the other one shows that behavior? Obviously, this one is an engineering curve, and the stress for the engineering curve is F divided by A0. In fact, the load divided by the original cross-sectional area. That's why we see the drop here. Okay? And this one is the load, the stress here is the load divided by the current area, not the original area, current area. Okay? So what's the difference between the original area and current area? The difference is that the original area A0 remains constant, but while we are applying the stress and the length changes, so the area in fact changes. The area, cross-sectional area, is not constant, but for the calculation of stress here we take it as constant, and here we take the current area. We take the current area, so F divided by current area, but because current area decreases as the length increases, because the volume remains constant for most of the metals, okay, under normal pressures and stresses. Therefore, we don't have any volume change. So if the length increases, the cross-section must decrease. Okay? So that's why this increases, because as F increases and the area decreases, okay, the ratio of F over A increases. So here it shows the stress increasing. That is the true stress strain. But here we see that we have a flat part of the curve, almost flat, and then it suddenly drops. Of course, it's not flat. This has a gradient. It's increasing. Okay, it's increasing, but very little increase we see here, and then we see drop. Why we see the drop here? Because the original cross-sectional area is used, but in fact the area decreases. Okay, so what happens when we use the original area? The load is proportional, of course, to the cross-sectional area, because as the cross-sectional area is decreased, the load applied on that becomes smaller to make a plastic deformation, because we have a smaller area. Okay, so the load decreases, but the original area is constant. So the load divided by the original area shows a decrease in here up to the fracture point. Of course, here it increases up to the fracture point. Okay, now we have shown here a correction for this curve. Why? Because as we said earlier, this is the true stress strain curve. We have used here the current area. So why should we correct it? This is the correct one. This is not correct. This is correct. But we need a correction here due to the necking. Okay, because as I said, at M, shown here M dot, we experience an instability, in fact, and it's not stable anymore. It's unstable. So this means that the necking is forming. Okay, so when the neck is formed, the area is not constant along the length, and this is the correction we make for that that necking. How do we make this correction? I will give you a report on this which shows you how to calculate this. Okay, so we have talked about this stress strain curve here. I think maybe enough, but I'll show you this another slide just to compare the compression and tension, because so far we have talked about tensile test. So what happens if we use a compression test? Compression test is very similar to tensile test, except the direction of the loading is reversed. In tensile test we stretch the specimen. In compression test we compress the specimen. As you can see, sigma and S for both of these behave in different fashions. What is this S? S is F over A0. Sigma is F over A. It could be seen here that for uniaxial tension, the stress, for the engineering stress, in fact, the behavior is like before, as I explained, because we are using the original cross-sectional area. The value of stress drops with the increase in strain or the extension of the specimen. But for the true stress, because we are using the current cross-sectional area, and current cross-sectional area is decreasing, therefore the value of sigma is increasing. And this is the behaviors, the difference with which we could see and we have shown in previous slides. But however, for the compression test, for the uniaxial compression test, as we can see, these are completely reversed. The stress as concerned with the engineering stress strain curve, it increases almost exponentially, and sigma, which is the true stress, but the increase is much less than this. This is a very sharp increase in the stress. The reason here again is the original cross-sectional area. For the compression, of course, is different from tension. As we know, as we compress the specimen, the area, cross-sectional area increases, while for the tension test, tensile test, the cross-sectional area decreases. So that's why here the behavior is very different. Also for the engineering strain and stress, behavior is completely reversed, because the original cross-section is much smaller than the current cross-section, while here is completely opposite. Here the original cross-section is higher than the current cross-section. So that's why we see the differences in the behavior of a